So today we're going to talk more about derivatives of a function, okay? And this is going to lead into what we're going to talk about next, but it's this sketching of a graph of a continuous function, okay? So a continuous function, and what that means is that there's going to be no breaks, so no removable discontinuities, no holes, no jump discontinuities, no vertical asymptotes, none of that, okay? And then we also know that f of 0 is equal to 0. So we want to draw the function, okay, with these properties. And this is also saying f prime of x is equal to 2 when x is greater than 1 and negative 1 when x is less than 1. So this point 0, 0 is going to wind up being right here. Okay, so that's the first thing we need to do is plot any known points, okay? Plot the point 0, 0, because we know f of 0 is equal to 0. Okay, now what this is telling me right here is that the slope for our function is always going to be 2 when x is greater than 1. So right here is x equals 1, right here. That's on the graph, x equals 1. And what I know about that, to the right of whatever point's on here, okay, my slope is going to have to be 2, okay? So for x greater than 1, the slope is always 2. Now, what type of function has a slope that's always the same? It's always constant. Well, that would be a line. So we're going to draw a line with a slope of 2. Okay? All right, so to the right of here, we're going to draw a line that has a slope 2, okay? And then to the left of it, right, for x less than 1, the slope is always negative 1. Well, that means the slope is always going to be negative 1. The slope is always constant, right? So that's a line also. So for x less than 1, the slope is always negative 1. So this would also be a line. Anything that has a derivative that's a constant is going to be a line, okay, with slope negative 1. That's what we're going to draw, okay? Now, which side of 1 do I start at? Now, I can't just draw this anywhere. And what's the giveaway is that this point is to the left of 1. And what do I know? For all x less than 1, okay, so that means to the left of 1, the slope is always going to be negative 1. So from right here, what we could do is we could draw a line through that point that would have a slope of 1. So we could go down and to the right, and that would put me right there. And that would put me right at 1. So that's it, okay? Now I could draw some more points by going up and left and just continue up and left, up 1 and left 1, up 1 and left 1, up 1 and left 1. And then I could go ahead and draw that part of my graph. Okay. And I know it has to go through that point because that's on the function, okay? And it just continues forever in this direction, okay? And double check for x less than 1, is the slope negative 1? Yeah, down 1, right 1, down 1, right 1, okay? Now, what else do we need to draw for this, for all of these properties to fit? Well, to the right of 1, we're going to have to draw a line with slope of 2. Now, we already know a point right at 1, so from there, we can just continue it, right? So we're going to go up 2 and right 1. That would have a slope of 2, up 2 and right 1, and up 2 and right 1, okay? And then I'm going to draw through there, okay? And that is our function. This function goes through 0, 0. It's continuous. There's no breaks in it. To the right of 1, okay, to the right of 1, the slope is 2. And to the left of 1, the slope is negative 1. And that's how you would do a problem like this. We're now going to move into what's called one-sided derivatives, okay? So a function, any function, we say it's differentiable on a closed interval from a to b, so start and stop, and closed dots on both. So that means it has endpoints. if it has a derivative at every interior point of the interval. So every point in here, we can take the derivative. And if the following limits exist. So the limit as h approaches 0, and it's hard to read. Let me try to autofocus again. It's so small, it's hard to focus on it. But that's a positive. So what that means is where h is approaching 0 from the right side of 0 of f of a plus h minus f of a over h. Now, this is called the right-hand derivative, okay? And here's what's weird is it's called the right-hand derivative because we need to go to the right of a and bring that point in. And that's why this one's called a right-hand derivative. I'm going to talk a little bit about it in just a little bit, okay? When I start, you see this grid down here, we're going to talk a little bit more. I have this zoomed in so that you can clearly see this, okay? Then this one is the limit as h approaches 0 from the left. Now, what that means is my h values are going to wind up being negative, okay? And because my h's are going to be negative, and I'm going to explain this several times right now, okay, in the next few minutes, because h is to the left of 0, it's negative. This really, it looks like we're adding h, and we're thinking of h as being positive, but because of the way we're approaching 0, this h is actually negative. So really, this is b plus a negative, which could be rewritten as b minus, okay? So this is going to cause it to go from the left, okay? So we're going to pick a point to the left of b because b is our right endpoint, and we're going to bring that point in, okay? And this is called the left-hand derivative. So to find a derivative, okay, we haven't been doing it, but really it's a limit. And if it's a limit, that means we need to look at the one-sided limits, okay? Now, we haven't had to do that until today, okay? And we're going to need to do it today because there's some functions that if you approach from both sides or from either side, they're not going to be the same value. That's actually what just happened on the previous problem, okay? Okay, so now we're going to talk about this, this graph right here. This left endpoint has to be A. And this endpoint right here, by what I said above, is B. Okay, so now what we're gonna do, we're gonna draw this a picture of this. Okay, so H is approaching 0 from the right, so I'm gonna go to the right and pick a point that's H units away from A. So let's say something like right here, and this would be A plus H. Now let's assume that this function is f of x, okay? Let me just draw it here. This is the function f of x. Okay, so this point right here, this left endpoint would be a comma f of a. And this point right here would be a plus h comma f of a plus h. Okay, and then what we're going to do is we're going to bring this point, this limit up here, this one right here, I should say this h right here, h is a positive number. Okay, so what that's going to do, if h is approaching 0, right, that's because h is a number to the right of 0. That means it's going to be positive, which would cause me to go to the right if I add h. And then we're going to let h go to 0. So what that does is it moves this point into this point, right? Okay. This next one, we're going to go b. Now, where is b plus h? Now, if we tried to find the derivative of b, we can't go out here to the right because this is a right endpoint and there's no more function out here to pick a second point. So what we could do is pick a point like right here. Okay, and this point right here would be, I should say, b comma f of b. I probably should have said that earlier. And then this right here, you might be thinking, oh, that's b minus h. No, it's not. It's not b minus h. It's actually b plus h. And you're sitting here going, what? Why? You went to the lab. That's subtracting h. Yeah, no, it's not. And here's why. Because h is approaching 0 from the left. That means this h value is negative, which means we're really adding a negative value, which really ultimately causes us to really make this b minus a value, okay? I shouldn't say h because it's no longer h if I change this to subtraction, okay? But right here, this h, this is what's important. H is a negative, and that's why we're writing b plus h. We're not wrong. I'm not making a mistake, okay? So right here, this point, because of the limit right here, that h is going to get closer and closer to 0, okay? And then that's going to cause us to move along the curve until we get right to that point right there. Okay, so that's a picture of these two, okay? And then let me slide this up. Actually, let me zoom out a little. I don't want to zoom out anymore because I want to say some more stuff. Let me scooch it up, scooch it up, scooch it up, scooch it up, scooch it up. Okay, there we go. All right, so now down here, a function has a two-sided derivative. Okay, so that means two-sided means that they have a derivative from both sides, okay? From the right side and the left side. Derivative at a point if and only if the function's right hand and left hand derivatives are defined and equal at that point, okay? This one right here is called, this is weird because it's on the right hand side, but this is actually called the left hand derivative. And this one over here, you would think it'd be the left hand, but it's not. It's the right hand derivative. And it's going to make more sense when we do this point, interior point, okay? So this is a right hand derivative. That's this one, okay? All right, so I'm going to pick a point. Let's pick this right here. Okay, and that's point C. And I want to find the derivative at that point. Well, I'm going to go, I'm going to add h to this h right here. So this becomes C plus h. Now, it's only going to be on this side if h is positive. So what that means is this one, which is on the right, it's on the right. The C plus h is on the right. That's why this is called a right-hand derivative, is the limit as h approaches 0 from the right. And that would cause this one to happen, okay? Of f of C plus h minus f of C all over h. Okay, and then we're going to do one on this side. And this one would also be C plus h. Okay, but how am I going to get it on the left-hand side? That's because I have to take the limit as h approaches 0 from the left of 0, which means my h's are negative, which means I'm adding a negative value, which would put me on the left side of C, okay, of f of C plus h minus f of C over h. And then we say this is equal to each other. And if this is equal to each other, then we say the function has a derivative at C, okay? So right-hand and left-hand derivatives are defined and equal at the point. So a function has a two-sided derivative and they have to equal each other, okay? Both of these have to exist and they have to equal each other, okay? Now, on an endpoint, okay, you don't have to have the two-sided derivative. You just have to have the one-sided derivative. So a right endpoint, we would need to do the left-hand derivative. And if that exists, that would be the derivative at point B, okay? And same thing for A. We would do a right-hand derivative, okay? Do you see now why it's called a right hand? Because this is the part that's causing it called right. And it's this right here, that's causing this one to be called a left-hand derivative. Hopefully this is making sense to you, okay? Because this is hard. This is hard for a lot of people, okay? Because you think of adding, you're thinking of h as being a positive value, and you're thinking of adding h here, and you're thinking, oh, that would have to go to the right. No, because h isn't positive, and that's why it's not, okay? I know I've said that several times, but it's really important you understand that and remember it. Because one of the first questions I'm going to ask you, and it's going to be similar to the problem I'm going to do next, is I'm going to say, show me that this is not differentiable by doing one-sided limits, okay? It's going to be a problem very similar to what you're going to see next, okay? So let's go ahead and do that. All right, so here we go with this next problem, all right? And I'm gonna tell you guys, this is the third time I've shot this video. I wanted it to be perfect for you guys, and I kept forgetting to slide my paper up. So I need you guys to say, Mr. Mitchell, slide your paper up. So every time I forgot to slide the paper up. Anyway, here we go. I had to tell you that. A little frustrated. Okay, so using one-sided derivatives, show that the function f of x, which is a piecewise function, it's x squared plus 6x plus 4 when x is less than -3, and 2x plus 4 when x is greater than or equal to 3, or greater than or equal to -3, I accidentally said 3, does not have a derivative at x equals -3. Okay, so a parabola is nice smooth curve. We're going to be able to take a derivative of that. 2x plus 4 is a nice straight line. You're able to take a derivative of that. So what happens is where it switches, okay? And where it switches at x equals -3. Now that's not always the case. Sometimes you can have it not differentiable in here, but this type of function is a nice smooth curve. That's this one right here. And the 2x plus 4, that's this one, okay? So we want to show that there's no derivative right here at x equals -3. Okay, and the way you can do that is by doing one-sided derivatives. Okay, so the very first thing we're going to do is we're going to do the right-hand derivative, and I'm going to look at my screen a lot so I don't forget to slide this up. Okay, so we're going to look at the right-hand derivative, and this is how there's no notation to state like there's not an f prime of a. You don't write f prime of a here because it's not really f prime of a or f prime of -3, because that would have to be the one, both sided limits would have to equal each other. That's a two-sided limit. Okay, so right hand derivative at x equals -3, and I'm gonna put a line underneath that. Okay, and we just jump right into the limit. Okay, and I'm leaving a little bit of space because I want to write something above this. Okay, so we're going to look at the limit as h approaches 0, but we want to do a right-hand derivative, so we want to go from the right. So that's positive. That's another way to look at it, okay? And then we're going to do f of -3 plus h minus f of -3 all over h. All right, so now we got to take a look at this, okay? Right here, this -3 plus h. We have to consider what h is, because h, right now, h is, we're looking at h being 0, right? Okay, so right now that's -3, but we have to figure out what piece we're going to put that into, okay? Because it's not -3. But which one is it? Because it says to use one if it's less than -3, and it says to use the other one if it's greater than or equal to -3. So -3 plus h is approaching 0 from the right. That would mean h is just a little bit bigger and positive, right? Which means when we add -3 plus that value right here, it's actually going to be bigger than -3, right? So -3 plus h, -3 plus h is larger than just plain old -3, okay? So that means we're going to write this as the limit as h approaches 0 from the right of, and we're going to put -3 plus h into, which piece do I use when it's greater than -3? And it's the line, right? So we're going to use a bracket, and then 2 times -3 plus h, and then plus the 4. I almost forgot the plus 4. And then minus. Okay, so what do we use when it's exactly -3? Because that's this one, right? And when it's exactly -3, we still use this line, right? 2x plus 4. You can also see right there the point, okay? So this is going to be 2 times -3 plus 4. And I'm going to close the bracket. I think it's always a good idea to use the brackets, okay, and a subtraction in between. when you're putting stuff this, you know, a plus h or whatever the number is you're trying to find the derivative of plus h, when you put that into the function over h. Okay, so this becomes the limit as h approaches 0 from the right, and this becomes -6 plus h, plus 2h, sorry, plus 2h plus 4 minus, and this becomes -6 plus 4, so that's -2, all over h, and then this is equivalent to the limit, because I have a little more room now because it's being condensed. H is approaching 0 from the right, and this would be 2h minus 2, and then plus 2 over h. That could be, I mean, you could write this also as -2 plus 2h. You'd be fine if you did that. This -2 and plus 2 cancel each other out. So then you're left with the limit as h approaches 0 from the right of 2h over h. Because this is a product, we can cancel, and that makes a 1. So this is the limit as h approaches 0 from the right of 2. Well, when you take the limit as h approaches a number of a constant, it's always that constant. So this is equal to 2. Okay? So what that's saying is the right side of -3, the slope is always going to be 2. Okay? The derivative is always 2. Doesn't matter what point you pick. Okay? And that makes sense. This was our anchor point where we were trying to find the derivative at. Okay? And I just said something that was wrong. I need to correct that. Okay, so right here, I said any point on here, and it's true, but really we're not doing any point, we're doing -3. So at -3, the slope is 2, okay? It turns out every x value would be the same, that's why I said it, but what I said was wrong, okay? Because we're finding it at -3, not every x value. Now think about this. If we take this point, this is our like our anchor point that I talk about, okay? And you pick any point to the right, and you draw a line through that, right? The slope is always going to be what? It's always going to be 2, right? If I pick this point, slope's 2. Pick this point, slope is 2. Pick this point, between that point, slope is 2. 2, 2, right? Doesn't matter what this one point and any other point on here, the slope is always going to be 2. All right? Okay, so now let's look at the left-hand derivative, okay? So I'm going to slide this up so I don't run out of room and I don't have to shoot this a 4th time. All right. It's frustrating. I frustrate myself a lot. Okay. All right. So this time we're going to do the left-hand derivative, and I'm going to have to slide this up and down because we want to refer back to the function. And I would just label it like this. I would just add x equals -3, okay? Okay, to be a left-hand derivative, we have to do the limit as h approaches 0 from the left of f of -3 plus h minus f of -3 all over h. And I didn't leave myself enough room. I'm going to squish it in here. Okay, so now what do we know about this -3 plus h? Because I need to decide, is that bigger than -3 or smaller than -3? Because that's going to dictate what function I put it into. So -3 plus h. Okay, now we got to think about what really is this h? So this is going to tell us right here. H is approaching 0 from the left. Okay, that would mean that our h values that we're putting in would be negative. If it's negative, that's -3 minus, right? And so that's going to actually make it smaller than -3, okay? So this time, -3 plus h is smaller than -3. Okay, so that means I'm going to slide this up a little bit, or slide it down, and I'll slide it back. That means if we're less than -3, that means we're going to be putting it into this quadratic right here instead of the line. Okay, I'm going to slide it back up. Okay, sorry, you can't see it. So the limit as h approaches 0 from the left, and this becomes, I'm going to use a bracket, and this is -3 plus h squared plus 6 times -3 plus h, and then plus the 4. Close my bracket. Because what our function said to do when it's less than -3 is square it and add 6 times the input and then add 4. And then minus f of -3. Okay, so f of -3 is, slide it up a little, down a little bit, I mean. Okay, this is said, we set this right here, this little piece right here says to use 2x plus 4 when x is exactly -3. So we're going to put it into 2x plus 4. We're going to put it into the line. Okay, all right. So this would be 2 times -3 plus 4 over h. All right, so now then that's equal to the limit as h approaches 0 from the left of, and okay, I'm not gonna do an area model to square that. We've done it a lot. This is actually going to turn out to be 9 minus 6h plus h squared. If you're not sure, trust me, okay? That's what it would come out to be if you drew the area model. And this would be -18, so minus 18 plus 6h plus the 4, and then minus, and that'd be -2. And that's all over h. So this is equal to the limit as h approaches 0 from the left. Cleaning this up, we'd have h squared. That'd be that one, right? And then we have 9 minus 18, which gives you -9, plus 4, which gives you -5. So -5, and then we have the minus 6h and the plus 6h, which cancel each other out. And then we're left with +2 all over h. So that means this is the limit as h approaches 0 from the left of h squared minus 3 over h. Okay, so we're approaching 0. The best way to do this is to separate this, okay, and make it h. This came from subtracting two fractions with a common denominator of h. And I'm going to tell you something. It's actually, let's just do it this way. I've done it over the years. I've done this a couple different ways. Okay, this becomes the limit as h approaches 0 from the left of h squared over h minus 3 over h. Okay, and this becomes the limit as h approaches, I'm watching my screen, h approaches 0 from the left of h minus 3 over h. Okay, so this becomes, if we try to do a direct substitution, we can do it right here because that would just be 0. But then we'd have minus 3 over 0, and that's a problem, right? So when recall back even from Honors Math 3, whenever we got just the denominator to be 0, that's going to cause either that value to be either infinity or negative infinity, okay? Now, this isn't a vertical asymptote because we're dealing with left-hand derivatives. If this was just a plain old function and I said find this limit, then yeah, it'd be a vertical asymptote, okay? So right here, if we try to do this, okay, this part's 0. This is getting to be 0, so that's a really small number. So we're taking 3 and dividing by a really small number, which is going to cause a really big number. But is that a big positive number or a big negative number? Okay, but think about what h is. H is negative, right? So we're going to be, this is like -3 over a negative value. So that's going to become positive infinity. So hopefully that makes sense. This right here is a negative value. Okay, so when we subtract a negative value, it actually becomes positive. That's a better way of explaining it. Okay, so this is going to be, we're subtracting a negative value. So this is going to be subtracting negative infinity because that would be negative infinity. and we're subtracting it, so it becomes positive infinity, and this is just plain old 0 because we can just plug it in. So this becomes positive infinity. Sorry if I'm long-winded. I really want you to understand this, okay? I don't think I understood it as well as like how I'm explaining it. I did not, when I was your age, I did not understand it quite like this, all right? Okay, let me show you why this actually makes sense from the graph, from looking at the graph, okay? So I'm gonna slide this back up, okay? And why one of them is 2, I've already explained that one, but why is the other one positive infinity, okay? So I'm gonna get a nice thin pin. All right, here is why. Okay, so we already did it from this side. So here was our anchor point, and that's still our anchor point, this one right here. And these are other points, okay? My dog Toby just walked in. You hear the clipper clatter of his toes? Say hi, Toby. All right. Okay, so right here, that's our anchor point. We want to pick a point because we're doing the left-hand derivative, a point to the left of this, all right? So if we pick, like, let's say this point right here, let's pick this point right here, okay? And we would draw a line through that, right? What's happening is this point's moving along. It's moving along, it's moving along, okay? So I'm gonna draw several of these points, okay? So that would be the line. This is like the line approaching what it's gonna be. And you see what's gonna happen? And hopefully you see, what do you know about all of these slopes? Well, they're all positive, right? And just before, okay, it's gonna be really, really steep. Just before it hits this point right here, okay, it's a really steep value, right? And look at the slope right before it. That's positive, right? You can tell it's going up from left to right, which would be positive slope, okay? So right when I get to exactly that open dot here, I'm connecting this dot up here with this open dot, which is perfectly vertical, okay? Which means your slope is either infinity or negative infinity. So why was it positive infinity? Because just before I make the vertical line, all the slopes were positive, okay? And so that means right when it becomes vertical, that's actually going to positive infinity, okay? Hopefully that makes sense. All right, so I'm gonna slide this back. I wanna talk about some other things, okay? Okay, so back to this, we can now say this, that because the right-hand limit was 2 and the left-hand limit is infinity, we can say that the limit as h approaches 0 from the right of f of negative 3 plus h minus f of negative 3 over h does not equal the limit as h approaches 0 from the left of f of negative 3 plus h minus f of negative 3 over h, okay, which means the one-sided limits don't exist. So now what this means is actually a couple things, okay? It would mean the limit as x approaches 0 of f of negative 3 plus h minus f of negative 3 over h does not exist, which also means, AKA, f prime of negative 3 does not exist. You guys, you may use D and E. I just can't. I do not know why. I just can't write D and E, okay? But D and E stands for does not exist, and everybody agreed. That's pretty much agreed upon. It's just a weird thing that I don't like writing D and E, okay? I know, I'm weird. All right. And when it gets late like this, I'm a little crazy too. Okay, let me slide it up. Hopefully you guys are having fun. So that's, it doesn't have a derivative of x equals negative 3, and that's what we showed, okay? All right, because we said that limit doesn't exist because of the one-sided limits. All right, guys, that's it for today, all right? I wanna say this, Friday, We are going to be doing more of these. So don't worry if it's like this right hand, left hand limit. I know this takes some time and it does get some getting used to. Okay. It does. And I know that. Okay. So I always allow 2 days for this. Okay. That means you have 2 homework assignments because you gotta jump in and try it the first day. Okay. And then come back the second day and like clarify stuff. Okay. All right, you guys, take care.